Okay, so our second speaker is Alessandro Chiesa. So I've been working for maybe almost 10 years.
It's 10 years,
slightly
yes.
less, but it's really amazing to see Ale starting with this grandiose idea of PCDs that kind of like say these checkable proofs that are composable, and you can actually compose proofs for many different people into short succinct proofs, and beginning looks like a folly, and then they became more theoretically sound and less practical, and now it's actually running. So it's like an amazing transition. And I think Ale was part of the people who really fathered this idea all along, and really happy to have him here.
Thank you, Ryan. Great to be here, and thanks for the organizers to put together this event. So today I want to tell you about a framework for post-quantum succinct arguments. Also want to highlight in the title the word framework, and I want to enthusiastically also second Yuval's sort of advocacy for a modular approach to constructing cryptographic proofs. I personally don't understand a construction until I see all the separate components, and in particular, I have taken out the information theoretic part. As a community, I don't think we would have been able to be where we are today without sort of a modular understanding of what we do. It's just the complexity is too high otherwise. So yeah. So here's the picture of a Zcash SNARG. The only reason why I have the picture is just so that we have some, for this talk, some common language and common symbols to use. As usual, you have a prover that takes some NP statement. You have a public function f, public claimed output, some given time bound. You have some private input x, okay, and it's trying to prove to the verifier that if you plug in the private input x on this public function, you really do get y within time bound t. Okay, and the key aspects of a SNARG are, again, this argument size that is very small, exponentially smaller than the size of the computation, and the verification time is also very small. Okay, so polynomial only in the description of the state of the computation, not the computation size. Okay, other aspects that are important, that it is publicly verifiable, so that once the proof is out there, anybody can check it. This is actually rather important in blockchain applications, because you can write your proof in a block, and everybody else can check it. Also, we have these system parameters that are actually necessary. You cannot have SNARGs without some sort of system parameters. And we all know sometimes they get annoying because they may or may not depend on trapdoors. And when they do, then we have trouble to sample them. So in the last 10 years, we have seen extraordinary progress in the cryptographic foundations of these objects, efficient constructions, implementations, applications. And in the peer-to-peer setting, while now for already several years we understand that consensus protocols are an important pillar to construct peer-to-peer systems with strong security properties, nowadays it's becoming more and more often that you find yourself designing systems where parties actually have to produce Zcash SNARGs, not just for privacy reasons, but maybe also for scalability reasons. And more Zcash SNARGs are becoming an indispensable tool for founding sort of peer-to-peer systems with strong privacy and also scalability properties. So this is to say that these Zcash SNARGs are here to stay, okay, in the peer-to-peer setting at least. Okay, if they're here to stay, I want to ask today a question. Which Zcash SNARGs protocols do you think will we use in a century, in 100 years? Okay, it's a reasonable question to ask, because if we want to build sort of all these peer-to-peer systems that are sort of we start thinking about as a public digital infrastructure, we really should think carefully about what cryptography we put in these systems. And I want to just make the simple observation that we actually have a shortage of options on this front. Because most efficient Zcash SNARG constructions ultimately rely on the hardness of extracting discrete logarithms. You might say, so what? Well, so as many of you know, over the past couple of years, there has been a worldwide huge investment in sort of what seems to be a renaissance of quantum computing. For example, China has a national program that, to the order of $10 billion. Europe also has a Europe-wide sort of program of $1 billion. And even President Trump understands this is important, okay? He will go and fund these things instead of other, more reasonable things like healthcare, right? And not only that, but 2 years ago, NIST not opened, closed a call for post-quantum cryptography, okay? Somehow, like April 2019, it's already late to think about a post-quantum anything, okay? Even NIST has sort of closed the call. And then, so what do, right? So all the discrete lock-based constructions are insecure against quantum adversaries. And if we're trying to build sort of long-term infrastructure with ZK-SNARKs, we should really ask ourselves, what are our options? We should study them earnestly, okay? So what do? So one option, as usual, is to turn to lattices. And indeed, there are some approaches in theory, sort of in the theoretical landscape, that actually can take us there, for example. So there is an example of a really nice works out of this is Dambonnet, Shai, Sahai, and Wu. 2 works in the last couple of years that they showed some beautiful compilers that take, in a modular way, notions such as linear PCPs or interactive proofs, and they combine them with some linear-only encryption that is based on lattices, okay? And these are they look like they would be post-quantum secure. The analysis hasn't been done, but it relies on sort of lattice problems that are plausibly so. The information theoretic part is information theoretic, so it's definitely secure against quantum adversaries. However, this approach still only gives us private verification, and either way, it seems like more has to happen in theory before this type of constructions will become practical. There's also other approaches that rely on lattices, but only give us square root sort of size in the proof. And that's pretty much where we stand today, unless I missed some references. And I want to say I think it's an excellent direction to try to look at sort of lattice-based ZK-SNARKs. I think there must be more that we can say than what we know today. The other approach that is what I will discuss today is to found ZK-SNARKs on symmetric key cryptography alone. Okay? We know that quantum algorithms are very good at reasoning in certain types of algebraic problems, especially sort of cyclic ones, like that they're related to discrete logarithms. But they're terrible at reasoning about a sort of bit-twiddling hash functions, okay, which is what underlies symmetric key cryptography. Okay, so today I want to tell you about constructions of ZK-SNARKs that are based just on symmetric key cryptography. So the way that we will get there is in a modular way by combining any cryptographic hash function. By that I mean just anything that can be modeled as a random oracle. So for example, SHA-256, Ketchak, Blake, you can pick your favorite. It doesn't really matter too much. The point is that these are primitives for which we don't really know what to say in terms of, we don't have effective quantum attacks. And on the other end, we will have some form of probabilistic proofs that is information theoretic. Okay? And even though today I'm specifically highlighting the post-quantum aspect of these constructions, I want to say that they have some really nice bonus. This particular framework for constructing ZK-SNARKs has nice bonuses. One bonus is that it will make only black box use of very lightweight cryptography. A lot of other constructions, like pairing-based SNARKs, putting aside the fact that they're not post-quantum, which is fine today. It's really fine. I mean, we are using them and they work. But they rely on expensive public key operations. For example, when you're running the prover, you're running sort of this huge multi-exponentiation operations that are rather expensive. You can optimize them, but it's kind of hard to sort of make them even more efficient because kind of they're not in hardware yet. Cryptographic hash functions are already in hardware today. Okay. Another bonus is that these constructions, because they only rely on a cryptographic hash function, they're so-called transparent, like meaning the setup of the system parameters is public coin. So you only need some sort of the only system parameter for us to use such a system is to agree on which hash function to use, on which initialization vector, and all these things, right? These are decisions that we can effectively make using public information. We don't have to rely on anybody to sample some trapdoors, put it in exponents, and then forget the trapdoor, okay? I will not highlight too much these bonuses throughout the talk. I'll mention them at a few key places, but today I really want to make a pitch sort of for post-quantum ZK SNARKs. Okay, so it turns out that all of these beautiful properties that seems like it's could be the bleeding edge of ZK SNARKs, actually were all satisfied by construction, the first construction of this ZK SNARK from the 90s. So we're going to come back, and I want to tell you about a construction you probably have seen, some of you have seen many, many times, but from today's point of view, this construction is really appealing, okay? And this is the Mikali construction, okay? So for that, so there's a theorem that says that there is a SNARG that is unconditionally secure in the random oracle model. And traditional viewpoint is that the random oracle is evil, and it is evil in some ways, and thinking of it as an evil construct has led to all kinds of beautiful works that try to kind of circumvent it and based SNARKs on alternative cryptography. And by the way, pairing-based SNARKs that we have today that are actually deployed in systems were, to some extent, the result of trying to avoid random oracles. So we had them because we thought random oracles were evil. And they are to some extent, but today I want to also propose this new viewpoint that because if we are able to build our SNARKs in a world of only random oracles, then we sort of have all of these great things. We have potential post-quantum security. By the way, I keep putting this asterisk in a sense that when I claim that something is post-quantum, we don't have a proof that it's post-quantum. Of course we don't, right? We don't ever have a proof of anything being secure, right? We're just saying that we don't have effective attacks against the scheme, okay? And also it has these other great advantages that are actually hard to have in many of the other constructions that are based on discrete logarithms. Do you want to say that random oracles are evil? Or no?
I want to say we just don't understand them. But
yeah.
You're comparing schemes with a proof to schemes without a proof, right?
Yeah. We don't understand random oracles. They may or may not be evil, but they certainly don't like to be understood.
Which random oracle? Random oracle for Ketchuk, for Shah, for which one? Random oracle would never be broken. But implementation would be other people.
But the question is is it because it's so obtuse, or is it because it's inherently secure?
Well, given some of the recent works, so the question is it because it's sort of hard to prove things about, or is it because secure? Is it really secure, right? So. For example, there are recent works that give more and more circumstantial evidence that in a variety of settings, very much related to this one, we can instantiate the random oracle given suitable.
Yeah, but exactly that's the point. So the instantiations we have today, not for this protocol, but for other protocols, actually, luckily, are based on lattices.
Yeah, exactly.
But assume that you had an instantiation of random oracles that actually was, discrete log based.
Then that would be a problem.
Then would be not post-quantum, but would be
so maybe let me kind of reflect it back and say, we can either try to take it easy and stay with random oracles, or in this direction, one can try to say, okay, let's try to instantiate random oracles for specific classes of constructions, for example, using this notion of correlation intractability, and make sure that our instantiations will be post-quantum, right? And that also gives us an avenue of attack that has, sort of more sound security guarantees.
What do you mean make sure that it's post-quantum?
Like, for example, if you use LWE to instantiate your correlation intractable hash function, then that might be plausible to assume that the overall system then as a whole will be post-quantum.
I don't want to derail your talk, but comparing LWE with the abstraction of random oracle and security in 100 years, it's not clear.
I am not mentioning LWE in this talk. It was injected by Ran.
I was making a face. You gave me.
I'm responding to Ran.
Yeah. Shh. Yeah, no, but. But all of these are great research directions, by the way. I think we should just think more about post-quantum ZK.
The thing is very important is if you, when you abstractions or approach if you can actually try to distill which properties
Yeah.
of the random oracle you are.
All soundness that I will talk about today, at least, is in the non-programmable random oracle. Okay, so we don't need programming random oracles, which is already good, right? Zero knowledge needs programmability, but whatever. At least it's not soundness. Okay, so the proof is the usual one that says, give me a random oracle on PCP, I'll give you a SNARG. By the way, I'll just mention some loose ends that I will ignore in this talk. They're actually important. And the fact that you can actually make sure that this construction is a proof of knowledge is very important, because most applications of SNARGs actually involve cryptography. And it actually is really important that your succinct proof is not just a proof, it's a proof of knowledge, okay? Or an argument of knowledge. Also, the SNARG can be made zero knowledge without sort of any additional cryptography. It can just be made so, okay? I will not mention these again. I just want to say that sort of these are things you can handle. Okay, so probabilistic and checkable proofs. Fortunately, I think Yuval already mentioned these in his talk. So, and also conveniently, Yael also discussed them in her talk. So here the picture. These are these proofs that you write down. These are not short proofs. These are actually very long proofs. But what's special about them is that you have random local checks. Okay, you have this query algorithm and this decision algorithm that spit out queries and gather answers, and they will sort of conduct a random local check on a long proof. Okay. So, and actually, the first paper on that sort of formulated that saw this connection of PCPs and delegation and computation, I had this really visionary quote that I keep putting out because it seems like it would have been written yesterday, but this was actually written at the beginning of the 90s. So in this setup, a single reliable PC can monitor the operation of a herd of supercomputers working with possibly extremely powerful but unreliable software and tested hardware. This is really exactly the way that we envision ZK SNARGs being used today, except that Babai411 and Segeni envisioned this for PCPs, and specifically actually mentioned this setup. And the point that this setup is unrealistic, okay? Like PCPs really feel like they're giving us this power of delegation, but they're not really giving it to us, right? Because you think you might have a protocol you can run, but it is insecure for the verifier to just ask the prover, say, what PCP did you write in your head? Could you please give me the answers for these questions, right? Because the security relies on first writing down the PCP and then the queries or samples. If that doesn't make sense, maybe an analogy. Guessing a coin flip is effective if you first say which side of the coin you want and then you flip the coin. You don't first flip the coin and then you say which, what's your guess, right? So this temporal difference is exactly what's happening here. You have to first write down the proof, which is kind of your guess for the coin, and then you flip the coin. So PCPs seem like they're giving us delegation, but they do so in this unrealistic model. And in this modular approach of an information threaded component and then cryptography, it's always like that. We have some sort of way of doing delegation in some restricted model. And then it's up to cryptography to pick up the slack and turn it into something we can actually use. In this particular case, for PCPs, the construction is really beautiful. This is work of Mikhaili that builds on work on Kilian. And it goes like this. The PCP will indeed, the prover will indeed in his head think of a PCP, except that it's not like a verifier will ask the queries directly. He will commit to it to produce a root using a Merkle tree. It will use the root to derive some randomness, simulate in his head the queries to the PCP, and then gather kind of this transcript and ship it off into a short non-interactive proof that contains the root, the answers, and authentication paths. The verifier will check the authentication paths are certified by the claimed root, and it will rederive the randomness from the root to check the answers, okay? Crucially, because the randomness is derived from the root, it cannot be, or at least one should prove that it cannot be, that the prover was able to choose the answers based on the randomness, because the answers are already inside the tree that was committed through the Merkle root, right? Okay, I just want to highlight some of the costs of this SNARG. On the right, I'm going to denote, I'm showing that L is going to be the proof length. Sigma is going to be the proof alphabet, and Q is going to be number of queries for the PCP. So the proving time here is just you're running the PCP prover, plain text. You're not running any cryptography. You're just running it. Okay? And an additive cost is that you have to hash the output. This is linear, by the way, in the proof, right? Because constructing a Merkle tree is linear in the number of leaves. The verification time is you just run the PCP verifier, and then you have some extra fast checks for checking authentication paths. The proof is just going to be the number of queries times the size of each authentication path. The authentication path is the answer, right? An answer is log the size of the alphabet plus the digest times log of the number of leaves, in this case, the proof of the PCP. Why am I writing these expressions? First, I want to highlight that the contribution of cryptography, or the overhead of cryptography, is really minimal. Your SNARG prover basically is the PCP prover. Okay? The cost of cryptography is essentially negligible. You're doing a linear amount of hashes in hardware. Okay? PCP verifier, same thing. Okay? It's checking a few authentication paths. It's nothing. Okay? So it really says that whatever you're obtaining through this construction is completely dominated by the costs of the running time of the PCP prover and the PCP verifier. The reason why I'm writing the argument size is because later I'm going to mention some exciting complexity conjectures that will imply nice things about post-quantum ZK SNARGs. Okay, so that's just the expression. And I'm highlighting the alphabet because these conjectures have to do with the alphabet. Okay, so this is the Mikali construction. You probably have seen it before. And it's plausibly post-quantum. Black box users of lightweight crypto, as I just remarked. And it's transparent because we only really need to agree on the hash function. OK, why aren't we using this construction all over the place in the real world if it has so many good things? Is it because the random oracle is a strong assumption? No. I mean, it is, but that's not why we're not using it. It is because PCPs are galactic algorithms in the sense that they don't, the poly-T efficiency for the prover is not quite enough. But actually, it's not quite the case anymore. Actually, many years ago in my PhD, I worked very hard on trying to make PCPs less than galactic. And we actually got somewhere. And we made them, I would say, merely expensive in a sense that really you can make the prover halt on some computations, but it will be 5 days later on a small computation. And so I don't think it's fair anymore to call PCPs as galactic algorithms. That's sort of only asymptotics matter, but it's not, they're still pretty expensive. So it's not something you would really use. So what do we do? So this brings me to kind of the last part of the talk, where even though we had this construction from the 90s that had all these beautiful properties, the one thing that was lacking wasn't even asymptotic. It was just concrete efficiency. Okay? But today, we actually have a new generation of ZK SNARGs in the random oracle model. And what got us there is basically thinking beyond PCPs, actually through a model that Yael mentioned in her talk of interactive PCPs, and even more beyond that, of something called interactive oracle proofs, which is a more general notion of PCPs, within which we can design much better probabilistic proofs. And then everything else falls into place, because our main issue was just that the information theory underneath. Everything else we're fine with. Okay? So let me tell you about this model. This was introduced concurrently 3 years ago together with Eli and Nick, who is actually somewhere here. And also in a paper that was mentioned by Yael in her own talk by Reingold, Rothblum, and Rothblum, where actually this model was used for constructing plain interactive proofs. But yeah, the picture for it is that we are just going to engage in a protocol where in each round there is a PCP. Okay, so the verifier sends some challenge, gets back a PCP, continues for a few rounds, again another challenge, another PCP, and at the end of the protocol, you do a random local check on all received PCPs. A special case of this is, of course, a PCP, right, where there is no first challenge and there is only one PCP. So that's the model. Now, you can define models all day long, right? So the models are only as useful as, if they're useful for something. So now let's convince ourselves that they are useful for something. So here's the picture. We're going to try to do the same that we did before of taking, instead of a PCP and turning it into a SNARG, we'll take an IOP, this multi-round notion, and take it into a SNARG, okay? And actually, not much is going to change, okay? So here is the IOP, this time IOP prover, simulated inside the head of the SNARG prover. It needs a first challenge. Okay, it makes it appear out of nowhere by hashing, maybe some session ID, or maybe the given statement, whatever, using the random oracle. That lets him write the first PCP. He can't send it. He's going to commit it using a Merkle tree. And then he's going to put this root of the Merkle tree into a hash chain that produces the next randomness. Why a hash chain? Because it's important that we have some temporal consistency. Like the previous protocol, there was a first PCP, then another PCP, then another PCP. We need to make sure these things line up properly in the prover's head. So we're going to put their roots into a hash chain. Okay? This hash chain lets us produce the next verifier challenge, which lets the prover produce the next PCP. We'll commit to it, and so on and so forth. This is just an example with two PCPs. In the end, you do the same thing. You gather all of the requested locations with the authentication paths, and you ship them off. And like before, you check all the authentication paths. Now, this time, they are relative to different roots. You make sure the roots are lined up in a hash chain that eventually produces the queries, and you check the answers. Okay? I'm hiding some details. When you have multiple rounds, there are some other things you need to many rounds you have to be careful about how you do this, but this is kind of at high level what happens. So we can still do it. I can give you just a random oracle or any cryptographic hash function, and we can compile an IOP into a SNARG. Okay. So this works. And the costs are really the same. Okay? Like, just with the difference that now L denotes the sum of the lengths, and Q denotes the sum of the queries across all oracles. But these are the same expressions that we had before. And like before, the IOP prover and IOP verifier are dominating the complexity of the SNARG. And also, by the way, like before, zero knowledge and proof of knowledge sort of just work out. OK, but so what? Now we have a more general notion. We have a more general notion, and we can construct SNARGs. We are missing exciting constructions to plug in, right? So that's kind of the next question. We said we've made a step. Now we have a bigger design space. This bigger design space is something we can support. And we have all the good things like before, right? It's still plausibly post-quantum. I believe it's still plausibly post-quantum. We're still making black box use of lightweight crypto. It's still transparent setup. We're still using random oracle. What has changed? Something has to change for this to be an exciting story. The point is that, unlike before, we're not stuck with very expensive constructions. OK? Does that make sense? So we have changed our design space to make it bigger so that we can have more freedom when we design our protocols. But we inherit all the good things that I discussed for the prior construction. All of them, really. So what has happened in the past, 2019. What has happened in the last 3 years is that we have much more IOPs that are much more efficient than PCPs. OK, that's the main thing that has happened. And also, let me say, it's not just what's been exciting is to notice that while we started out with expectations of only improving concrete efficiency, what has actually happened is that we found all kinds of settings where we can actually get even better asymptotics, OK, than PCPs. By the way, you might wonder, like, why didn't we do this a while back? Okay, most of this is, to some extent, research that could have happened 10, 15 years ago. Okay? Well, first, I guess there was less of a need for wanting so deeply and viscerally efficient SNARG constructions. But also, kind of looking back, it's kind of unclear why we insisted for such a long time on PCPs as the basis of constructing succinct arguments. Because when you look at this construction and you see the ease with which it's much easier to construct IOP protocols as opposed to PCP protocols, that feels like it's kind of the right way to do it all along. Okay? So that seems to be a bit of a historical sort of, I would say, inefficiency. So I will just spend a couple of slides to tell you a little bit about IOP frontiers, what has happened in terms of constructions that we plug into this framework. There's been a flurry of research in the last 3 years studying a number of aspects of IOP constructions. And this has introduced sort of many new techniques. Here are some keywords, things called like the interactive proof composition, univariate sum check, auto-domain sampling, algebraic linking. Oh, these are just keywords for you to look up. And the point is that this body of work has given us a lot of results, including asymptotic statements that are just out of reach of IOPs. Let me give you 2 examples, okay? 2 examples of asymptotics that we know how to do with IOPs, but we don't know with PCPs. For example number 1, problem of constructing zero-knowledge PCPs. These are PCPs where if you query them at a bounded number of locations, you learn nothing, okay? We can construct zero-knowledge PCPs. This is a result, classical result from the 90s. That construction actually has quadratic size. Remember, quadratic in this racket is bad, right? You always want things close to linear. Separately, we also know how to construct PCPs of quasi-linear length. T polylog T. We don't know how to achieve both together. It's a great open question. We don't know how to achieve zero-knowledge PCPs that are quasi-linear. Why do we care? Because we want to plug them in the Mikali construction. I don't know how to solve that question, but with IOPs, you give me 2 rounds, we can achieve zero-knowledge and quasi-linear together. And that's something you can plug into the compiler for IOPs. So that's an example of a sort of quadratic gap between the 2 models. I'll give you a different example, okay? Let's take the NP-complete language of circuit satisfiability. The best proof length you can achieve for a PCP for this language is linear. Linear in the circuit size. But we don't know how to achieve it with a small query complexity. That you always want to have the best proof length and the best query complexity. Why? Because the proof length kind of is a proxy for the complexity of the prover, because he has to produce this proof in his head. And the query complexity determines the argument size for the SNARG, because we have to communicate all these queries with the authentication path. One of the major open problems in PCP land is to achieve the best trade-off of proof length and query complexity. Can we achieve linear PCPs with constant query complexity? We have no idea how to do this with PCPs. With an IOP, it turns out you can do it with 3 rounds. We can achieve IOPs that have 3 rounds, so PCP, challenge, PCP, challenge, so PCP, challenge, PCP, challenge, PCP, so 3 PCPs, where we have both linear proof length and constant query complexity. This is the best trade-off of linear proof length and constant query complexity. So these are just 2 examples of things that just happened in the last 3 years. Give it more years, and we'll be able to do even more. And so what has happened is that there has been a very exciting sort of back and forth between asymptotic improvements in IOP protocols giving rise to concrete improvements in IOP protocols in terms of implementations, and then sort of getting stuck somewhere else, formulating an interesting theoretical questions, coming back to the basics, and making more progress in the theory of interactive oracle proofs. And through the transformation, anytime you make improvements in concrete efficiency of IOP protocols, you will get improved IOP-based SNARGs. Okay, this kind of post-quantum, within this post-quantum framework. To give you a sense of the progress, if in 2017, shortly after we introduced IOPs, we had SNARG sizes that were tens of megabytes, as opposed to even more for PCPs. Since then, there has been a rapid decrease or in SNARG size improvements, okay, in really orders of magnitude. And each of these improvements, you can really point to certain techniques and tools, new ideas that came up through theoretical works, and how these sort of contributed to our body of tools in IOPs and pushed the proof size down. These days, we have IOPs that will give you still pretty large proofs on the order of, say, 100, maybe 50 kilobytes. And this is not the kind of proofs you would put in every block, but they're already practical today for batching applications. So you take a bunch of transactions, and maybe you produce one SNARG proof that summarizes what has happened in all of these transactions, okay? these, for example, applications for scalability. And the frontier really is, can we get to be competitive with discrete logarithm-based constructions? Can we get underneath 10 kilobytes, underneath 1 kilobyte? Okay? That's really the question. It's already great that we are at 100 kilobytes. This is already, I think, sort of gives us hope for post-quantum SNARKs in the real world. So here is, for example, a graph. This is, I didn't draw it. It's like, a machine plotted it on measured data. So this is actual interactive oracle proofs running. This is a post-quantum ZK. All of these are post-quantum ZK SNARKs across 3 different papers. What I want to show here is argument size against number of gates in the circuit. And I want to show you is that, you know how asymptotic results, you worry they start mattering too far out into infinity? Here I'm covering from 1,000 gates to 1,000,000 gates. It's not a lot of gates. Okay, I'm starting from very small circuit to smallish circuits. I mean, 1,000,000 gates is not a large number. And already in this interval of instance sizes very close to 0, we can really see constants and asymptotics mattering. So it means that we have a very fine-grained understanding in sort of rather explicit constructions where we don't have noise close to 0, right? The features of our constructions matter on instances whose sizes we care about. So that's important. Okay? So all this sort of complexity theory behind the scenes is working effectively at sort of human understandable instance sizes. Again, I want to highlight that the discrete log-based constructions are doing still much better. The sort of for example, in the pre-processing SNARKs, the shortest proof size due to Jens Groth 3 years ago, it's 128 bytes. That's very small. Okay, it will take us more years to get there with post-quantum technology. And that's why we used pairing-based SNARKs today. I want to leave you with a complexity theory question. So, I'm coming back here to the expression of the argument size all the way to the right there in terms of the query complexity, alphabet size, and proof length. And by the way, kappa is the security parameter. And I want to plot here the features of the best, sort of let's call it practical construction with nice constants. What it has is linear proof length. The alphabet is also linear in the instance size, so log of that, which is what you read when you read an alphabet symbol, is log n. The query complexity for soundness 2 to the minus kappa is on the order of k log n. So this gives you overall a proof size that is k squared log squared n. And if you do some back-of-the-envelope computations with some reasonable parameters, this pretty much works out to be like on the order of several hundred kilobytes. So this back-of-the-envelope computation is consistent with the measured data. You should be paying several hundred kilobytes for this expression. Best known asymptotics, actually, we have some probably very ugly constant, unspecified, but we know how to do it, where the query complexity can go down to order of k. So this would shave off of a log n in the argument size for the SNARK. An open question is to come up with constructions where the explicit constant is a good one. This would already, I think, improve by more than an order of magnitude the sizes of post-quantum ZK SNARKs. The holy grail would be something that we could call the sliding scale conjecture for IOPs. Sliding scale conjecture is one of the other major open problems in the area of PCPs. This basically asks, if I'm going to increase my alphabet to grow with the security parameter, can I keep number of queries to be constant? Okay, why would I care about that? Because if you look at the expression up there, for the size of an argument, through this construction with Merkle trees, because I have these Merkle trees, the authentication paths, and I'm paying for them, I would rather ask large alphabet, with each query I want to retrieve as much information as possible, because for each additional query that I ask, I'm going to have to pay for an additional authentication path. Okay? So the setting of parameters for the sliding scale conjecture is kind of optimal for what you would want to do in Merkle tree-based constructions. And if you do back-of-the-envelope computations for that expression, that is something that would actually give you on the order of 1 kilobyte proofs. Okay, so it is not unthinkable that post-quantum ZK SNARKs based on symmetric key cryptography could one day get us to 1 kilobyte size proofs. Okay, so that's the point that I'm saying here. Okay, and it's all about thinking about the underlying complexity theory. There's nothing that cryptography will help us with this construction. There are other, I just wanted to mention that there are other papers that study for IOPs. Let's use other type of cryptography. For example, discrete logarithms or class groups. We can compile these things and get even smaller proofs. Okay. All right. So what I've told you today is a framework for post-quantum ZK SNARGs. It relies on this information theoretic component of interactive oracle proofs. There are IOPs are much more efficient than PCPs. There's no reason to design a PCP if you're designing efficient ZK SNARGs. And there is still lots of room for improvement to achieve very small proof sizes. And if you want to play with some of these things, there is actually a library. It was mentioned on Wednesday, libiop. It's available at libiop.org that actually implements this framework in a modular fashion, also in code. That's all I have for you today.
More questions? Yes.
Can you say, is it easy to say a word or two about how you construct these IOPs, like high level?
Sure. Yes. So the question is, I guess you had the microphone. Of course.
Rather give another 40-minute talk.
Please, before the break too. There are two main components. One is all the practical constructions we have today are based on the Reed-Solomon code. Okay? So you use that as a stepping stone. So first you take your problem of interest and you want to do a randomized interactive reduction from, say, satisfiability of a circuit to a testing proximity to the Reed-Solomon code. Okay, so you take your witness and instead of encoding it using Reed-Muller, you encode it with Reed-Solomon. Instead of doing the usual sum check, you do things like univariate sum check. And at the end of all of this, you're left with the question, here's a few code words. Let's make sure that these code words are close to Reed-Solomon. So that's one part. The second one is you have to have efficient low-degree tests for the Reed-Solomon code. And that's a problem because the Reed-Solomon code is not locally testable, right? So, and an inflection point happened 2 years ago when a particular protocol was designed called FRI. Stands for Fast Reed-Solomon IOPP. IOP of proximity, and it's a beautiful protocol. It's a logarithmic round. It looks like the fast Fourier transform applied to proximity testing, and it's a very, very efficient proximity test for the Reed-Solomon code. So that's a workhorse underneath all of this. It stands underneath all of these protocols, and that protocol itself I think has still rooms for many improvements. More questions? Or? Oh. The prover time is, we are today at a point where I think it's basically optimal, but we don't know how to prove that. It is n log n in arithmetic complexity. So if your instance size has size n, then the prover will run in time n log n arithmetically. And the main reason why it will run this much is because it's running fast Fourier transforms underneath. And short of finding sublinear time encodings for this type of polynomial-based codes, then we don't know how to make it run in linear time. Thank you for your attention.
Thanks. Thank you.